try working a problem?
Sure, because now I have this the concept a little bit more. What about actually mathematically solving for things? Because really the only way that we can really measure entropy is through math. I don't, everything that deals with all this stuff is really math. You can conceptually look at something and say, oh, this is more entropy, but it's all a scheme to calculate all of these things, you know, like that's just what we've done as man. We try to understand certain things, so we try to turn it into numbers to understand it, which makes sense, right?
It's, yeah.
No, I'm just kind of being sarcastic about it, but anyways.
So this is what they've given us.
So these are all the equations that sum of the change of entropy of our products minus the sum of the change of entropy of our reactants. Oh yeah, got those little circles.
So this is going to sound bad, but what are those things?
Oh, this little sign?
Yeah.
It means not. At least that's, I think it's the Greek name for it.
Okay.
I think. No, I might not be right. Which I feel silly because I'm getting recorded, you know, judging my intelligence. But anyways, so this symbol simply means, I like to think of O as like, well, before when you saw it in kinetics, when you saw this symbol, and it was actually down here like this.
Oh, okay.
Whenever I think of O, I think of original, but when it's in this term, it's actually for a specific circumstance, where this O means, okay, if we have 1 mole of this product at a certain temperature and pressure. So these numbers are found through through a table that someone has given you. Well, at least these numbers are here. So there's a table that people give that they've calculated entropies, but they've calculated only in a certain scenario where they took 1 mole of like a gas and they did a bunch of reactions just with 1 mole of it. And then they came up with all of these numbers.
Okay.
So then that little symbol just is saying, in standard conditions, this is the entropy for this. So then this symbol here, the sum, saying, okay, we have a particular reaction happening. We say, okay, A plus B makes C. Well, how do we really know what numbers to use? Because what if we're doing this reaction in a lab, and we only have, let's say we have 0.7 moles of this and 3 moles of this, and we end up making 2.5 moles of this, right? And this is not accurate at all, but you can see how they're not necessarily, I mean, depending on the scenario we're in, I mean, it would be different. Someone else probably had less than you or whatever. So then how do we figure out what numbers to really use? Well, scientists then did it for us and only took 1 mole of this, 1 mole of that, and 1 mole of this, probably at 25 degrees Celsius at 1 ATM, did all these reactions, and then wrote this big giant table with all of the delta S's, H's, and G's.
So those are amounts will be given.
Yes. So you then say, okay, the sum of, that means sum. So it's simply saying the sum of the products, or the sum of the delta S's of the products, minus the sum of the delta S's of the reactions.
Oh, okay.
So if we said, let's say we looked up a table and found the delta S for naught of S in standard conditions for A was 393 joules per mole Kelvin. I think that's what it would be. And then for B was negative, no, it wouldn't be negative. Positive, and these are all positive, positive joules per mole, 100 joules per mole Kelvin, and then this one was 150 joules per mole Kelvin. So now we have these numbers at 1 mole of this substance at 25 degrees Celsius. This is how much entropy it would contribute when it reacts. So then we say, okay, well, if we take the sum of this, so let's say there's 1, so the sum of all this minus the sum of all this, that will give us the sum of the delta S of the total reaction. So am I making sense?
Makes perfect sense.
If there's 2 of these then, you then have to take into consideration, oh, I have 2 moles of A. All I have to do then is when I'm adding all these up, you just multiply this by 2 and then add it to 100, so you get,
And we've done that with enthalpy before too.
yes,
So it's just,
same thing,
it's okay.
same thing, it's very simple. Now, okay, yeah, what's it, because I could keep going on this, but, because this is just one way of doing it. Because if we've been given a bunch of values, then we can, and it's really easy to do that. Because sometimes we may have been given just the delta H of some kind. There's another equation that we can use.
Is that free energy?
Have you talked about gives free energy yet?
Yeah, I understand. Because I was just thinking, like, what if we're told to find entropy? But
Yeah, you have those
So
other
you can
equations
just
here. I'm going to erase this. I think you understand enough. We have the other equations of delta G equals delta H
we
minus
still
T
see this
delta
because we're doing this in bio right now.
yeah, that's nice.
It's something-
Yeah.
One less thing to study.
So it's nice because these then tie into this idea of Gibbs free energy, which is spontaneity, or you could think of it as the ability of a certain substance or reaction to happen without any outside help, you could almost say. Or the idea that, just like how this black powder, if I throw a match on it, it just goes. The amount of energy that the black powder needed at first was simply just whatever the match incorporated to it. And then, once it happened, it just goes. So, of course, the idea of delta G is more complicated than we're studying it. But whenever you see negative, it's really simply, oh, well, this reaction can just keep happening on its own.
Spontaneous.
If it was positive delta G, then it would happen. It wouldn't happen in that direction unless you incorporated more energy into it to like make it happen. Like photosynthesis, which I think you'll talk about in Bio-180. You need energy from the sun to make photosynthesis happen. It doesn't just happen. And in cellular respiration, though, is a good example of a negative delta G, where now you have glucose being broken down. So that is an idea of a spontaneous reaction, and then photosynthesis is non-spontaneous. So delta G then incorporates this idea then of entropy, temperature, and delta H. Those all are contributors to this. So that can kind of help you then understand maybe how delta G works. If you have a really high, if you have a really exothermic reaction, then think about that. Energy is being dispersed, it's exploding. Let's think of like the bomb again. If it's highly exothermic, if you're by it, you don't want to be too close to it. So then if a lot of energy is being dispersed out, well then you can probably guess that is it going to be increasing in entropy or decreasing in entropy?
It's probably going to be increasing.
Right, I mean it's exploding and destroying stuff. Chaos is everywhere. So then if this was just happening at 25 degrees Celsius, conveniently, and we have this, well, yeah, it's going to be positive. So if you think of this reaction, we have a negative number here, a positive number here, and you've probably gone over this idea. But I'm trying to help you see conceptually how it makes sense. We have a negative number minus a positive, which makes it a heck of a lot more negative, right?
Yeah.
So this is always going to be negative in that case.
Okay.
So you can think of that. What are examples of it? Well, possibly black powder exploding. I mean, it's never going to decrease in entropy when it explodes, right? And it doesn't make any sense. So there's a bunch of other examples. the one that is probably the hardest one to think of is this one, where you have a positive delta H, negative delta S. And it's, I mean, yeah, this is, well actually no, this one's easy, I'm sorry. This one will always be a positive number.
So when they're positive, positive, and negative, 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 they're a little weird.
Yes.
Because they're both, they could be spontaneous, it just depends on
The temperature.
temperatures.
And that's the only, this is the only thing that can help you here to know that. And then you can use that equation to solve for temperature, to know that exact temperature where if you make delta G 0, right,
Yeah.
you can then isolate T. So if we have 0 for delta G, what does that mean? What state is the reaction in?
Equilibrium.
Equilibrium. There is not a change in energy, there's not a change in exothermic or endothermicness, and there's not a change in entropy. It's just constant, 0, that's why delta G is 0 at equilibrium. So if we make it 0, we can solve for T for the equilibrium state of it. I don't know if that makes sense. When we have our delta H and delta S, and we want to eventually make delta G 0, well, make it 0 and solve for T. Now we know the temperature. So then, depending on whether this is positive or negative, you can then say, okay, if I have positive delta H, positive delta S, and I end up getting, like, let's say the temperature is 393 Kelvin or something. So in the case of positive numbers, what do we need then our temperature to be to make it spontaneous? So we have positive, positive, 393 Kelvin. That's when this is 0. So what temperature do I need? Above it or below it?
It's going to be above it, isn't it?
How come? Just look at the map.
Yeah.
Positive minus a positive. In the case of this, we'll say this minus this is 0, right?
Okay.
When the temperature is 393 Kelvin. But what if I make this 394 Kelvin?
It's going to be slightly spontaneous.
Very slightly spontaneous, because you do positive minus. Now, positive minus a number that makes it negative.
Okay.
Now, it's a negative number for delta G. But if you go to 392, it's going to be positive. Does that make sense?
Yeah.
So then if you're thinking in terms of negatives, so now this is negative and negative. So you have a negative minus a negative, which makes it positive, right?
Mm-hmm.
Well, this number. And if we said that this was negative and this is negative, this minus negative is positive, and let's say it's 0, and let's say the temperature now is like 10 Kelvin, really small. Because this is more accurate, because, anyways, we'll talk about that in a second. So if we have 10 Kelvin as our answer, and it's 0, what if I go to 11 Kelvin? Negative minus a negative. But now I have a negative minus a negative that will make it now positive. So if we go above this temperature, it will be non-spontaneous. If we keep going down though, say 9 Kelvin, now it's going to end up being a negative number. Because now this number is bigger than this. Because you can think of these two as kind of separate. This is separate from these two together. As long as you make one of those bigger, or smaller, excuse me, in terms of negativity. If you make it more negative, then this will be negative. If one of these is bigger than the other, or more positive, then it will be positive. I don't know if that helps separating those two.
It does, yeah. I think I have free energy down. But I think it's interesting, I just, entropy. I don't even know how they come up with stuff like this sometimes.
You don't even know what?
I don't even know how they come up with stuff like this.
Well, you can study it, the guy who did it. I don't